Welcome to you all to this MOOCs online video course Theory of Yarn Structure. Today we will start module 8 Tensile Mechanics of Yarns. Mechanics deals with the study of force stress strain relation. In this module, first we would like to learn about the tensile mechanics of parallel fiber bundle. Afterwards, we would like to learn about stress strain relations in yarns. So, we will cover these two aspects under this theme tensile mechanics of yarns. Now, what is an ideal fiber bundle? An ideal fiber bundle consists of lot of fibers. Where the fibers are straight, they are all parallel and also they are parallel to the axis of the bundle. When we apply force to such a bundle, we assume that all fibers are gripped by both jaws of a tensile tester. And we also assume that the mechanical behavior of a given fiber is independent to the mechanical behaviors of all other fibers. So, by an ideal fiber bundle, we assume the bundle consists of numerous fibers where all the fibers are straight, they are parallel to the axis of the bundle, and when we stress such a bundle, then we assume that the all fibers are gripped by both jaws of a tensile tester and the fibers are mechanically independent. That means, when we apply force to a fiber, so the behavior of this fiber is independent to the behavior of other fibers, they are mechanically independent. Now, we talk about the stress of one fiber, then we will talk about the stress of an ideal fiber bundle. So, let us first talk about one fiber. Here is one fiber and there is a fiber bundle. So, what we see here, these are the jaws of a tensile tester. A fiber is gripped by both jaws of the tester, and here the distance between the jaws is h. When we apply a force capital S, as a result it elongates. So, the length becomes h into 1 plus epsilon, where epsilon is the elongation. Similarly, we consider a bundle, an ideal fiber bundle, where the initial distance between the jaws is h. Because of application of a force S subscript summation, this bundle extends, the fibers extends, and the distance between the jaws become h into 1 plus epsilon. So, let us now analyze the situation in respect of the mechanical quantities. Number of fibers first. How many fiber here we consider? 1. So, here it is 1. How many fibers we consider here? Say it is small n. Now, tensile force. What is the tensile force we consider here? Capital S. And what is the tensile force we consider here? Capital S subscript summation. What is the force strain relation here? Force strain relation here, S is a function of strain, and here it is a summation, force is equal to, is a function of strain. What is the strength of this fiber? As we know, strength is the maximum force at which fiber breaks. So, here we consider P, which is basically maximum of S. Similarly, here the strength is P star, P subscript summation, which is also maximum of this, and the last quantity is breaking strain or strain at break. Breaking strain. Suppose breaking strain is here small a. What does that small a means? P will be obtained when the breaking strain is A. Similarly, here it is A subscript summation, this will be obtained under this situation. So, these are the symbols we are going to use. Now, we will consider two cases. In the first case is very trivial, where we will assume all fibers exhibit identical characteristics of stress strain. So, we will analyze what will be the mechanical tensile stress, tensile strain in such a bundle. So, this is a case 1, very simple case. We assume all fibers have same force strain relation. All fibers have same force, that is strength. They have same breaking strain. What does that mean? That means all fibers are identical so far their tensile characteristics are concerned. In such a situation, the following relations are valid. We will be able to multiply them. Similarly, strength will be equal to, strength of the bundle will be equal to number of fibers n into strength of one fiber. Similarly, breaking elongation, breaking strain of the bundle will be equal to breaking strain of the fiber. This is a very idealized situation. Now, we will make it little complicated. We will come to case 2. In case 2, what we will consider, a bundle consists of two types of fibers. Say cotton, polyester, right. Now, then all fibers of one type say cotton or polyester have same stress strain force strain relation, same strength, same breaking elongation or breaking strain. So, if we consider cotton fibers, all cotton fibers have same force strain relation, all cotton fibers have same strength, all cotton fibers have same breaking elongation. If we consider polyester fibers, then all polyester fibers have same force strain relation, all polyester fibers have same strength, all polyester fibers have same breaking strength. However, the tensile behaviors of cotton fibers is different than the tensile behavior of polyester fibers. Of one type of fiber is different than the tensile behavior of other type of fiber. So, it means tensile behavior of all cotton fibers, though they are same, but they are different than the tensile behaviors of all polyester fibers, though all polyester fibers exhibit same tensile behavior. So, now you will consider such a bundle of fibers. So, it will be something like this. Suppose this is the upper jaw of a tensile tester, this is the bottom jaw of the same tensile tester. Now, if I have one fiber say red color, all straight parallel to the axis of the bundle, then there will be other type we will indicate by blue color. Such is the bundle. What will be the tensile behavior of this bundle? This problem was theoretically solved many years ago by one researcher. His name was W.J. Hamburger. So, the theoretical concept what we are going to discuss now for this kind of bundle are also known as Hamburger's model. Now, before going to the detail of the model, let us define the symbols that we are going to use in Hamburger's model. So, variables, fiber material or fiber, one type number 1, second type number 2. First, about fiber fineness. For type 1, we will denote it by T subscript 1, for type 2, we will denote T2. As an example, if a fiber bundle consists of cotton and polyester fibers, then T1 may denote the fineness of cotton fiber, T2 may denote the fineness of polyester fiber. Then second is force strain relation. For type 1, S subscript 1 is a function of strain, S subscript 2 function of strain. breaking strain of fiber or strain at break of fibers. Suppose this is A subscript 1 and this is A subscript 2. These two will be different. So, A subscript 1 can be less than equal to A subscript 2. So, this is a very important consideration here. Then we come about fiber strength. Fiber strength of type 1 P1 which is equal to S subscript A1, because if this is the breaking elongation, so function at breaking elongation will be equal to strength. Similarly, P2 function is S2 and breaking elongation A2. Now, number of fibers. Suppose this is N1, this is N2. So, total number of fibers in the bundle N N1 plus N2. Mass of fibers. Suppose this was your M1, this is your M2. What is the total mass of fibers? M1 plus M2. Now, mass fraction of type 1 M1 by M, let us say this is G1 and here it is M2 by M which is G2. What will be summation of G1 and G2? G1 plus G2 is equal to 1. Right. So, these are the characteristics of two types of fiber, 1 and 2. Now, we will consider the fineness of the bundle. Say bundle fineness we will denote by the symbol T, which is equal to mass per unit length. What is the mass of bundle? Small m. What is the length? Small h. So, m by h. Okay. So, all characteristics, if you see subscript 1, they denote to type 1, say cotton. There will be some characteristics which will have subscript 2, all those characteristics are related to type 2 fiber, that is polyester, and there will be some subscript, there will be some variables without subscript, they are common to both. Now, we consider this kind of stress strain, force strain curve of fiber. Of fiber. As I said you, two types of fibers, 1 and 2. Suppose this is the force strain curve of type 1 fiber and this is the force strain curve of type 2 fiber. So, type 1 and this will be type 2. The stress strain behaviors of these fibers are very different. However, all type 1 fibers have same stress strain behavior, all type 2 fibers have same stress strain behavior, but type 1 fibers have different stress strain behavior than type 2 fibers, right. Now, if we look carefully to this graph, A1 is the breaking strain of type 1 fiber. However, at A1 type 2 fibers do not break. Type 2 fibers have a force S2 subscript A1. At higher elongation A2 all type 2 fibers will break. So, their breaking force is P2. P1 is breaking force of type 1, P2 is breaking force of type 2. So, this is what we see. Now, what we have to now consider? We have to consider if this is the fiber stress strain behavior, then what will be the behavior of the bundle. So, first we need to know how many type 1 fibers are present, how many type 2 fibers are present. So, in order to do that, let us say M1. What is M1? M1 is mass of type 1 fibers. So, that is equal to G1 into M. M is mass of all fibers, G1 is mass fraction of type 1 fiber. What is the fineness of type 1 fiber? Single fiber fineness. So, what is the fineness of type 1 fiber? It is the mass of all type 1 fibers divided by length of all type 1 fibers. So, mass of all type 1 fibers is M1 divided by length of all type 1 fibers. What is the length of one fiber? Small h. How many fibers are present? N1. So, what is the total length? N1 into h. Right. If we substitute M1 by G1 M N1 into h, we can write it further. G1 by N1, M by H is bundle fineness into T. T is bundle fineness M by H. So, N1 is equal to G1 capital T by small t1. So, how many type 1 fibers are present is possible to calculate using this formula. Now, imagine in a textile company, we blend fibers in terms of their weight, their mass. So, generally mass fractions are generally known. So, G1 and G2 are known quantity, they are readily available quantities. Capital T, what is the count of the sliver, what is the count of the roving, what is the count of the yarn, these all quantities are generally known. What is the fineness of fiber is also known. So, capital G1, so small g1, capital T, small t1, these are all known quantities. So, by using all known quantities you will be able to calculate how many type 1 fibers are present in the bundle. Similarly, we can write N2. is equal to G2 capital T by T2. So, by using these relations one will be able to calculate how many type 1 fibers, how many type 2 fibers are present in the bundle, right. So, now we come back to this, we have to analyze the situation. In order to analyze this situation, what we do? We divide this region into 3 regions. First we consider what is happening at when the elongation is less than or equal to A1, then we will consider what is happening when the elongation is in between A1 and A2. Third region we will consider when the elongation is greater than A2. So, these 3 situations we would like to analyze. First is this interval, epsilon is less than or equal to A1. So, this situation. So, when they are at equal to epsilon is equal to A1, the force exhibited by one type of fiber will be N1 P1. So, what will be the force at elongation A1? N1 times P1 plus type 2 fibers are also stretched. What is the force coming from type 2 fibers? At this strain, this is the force, and how many type 2 fibers? N2. So, N2 this. If we substitute N1 from here and N2 from here, what we will see is G1 P1 by T1 plus G2 S2 A1 by T2. So, this is how it can be calculated. Now, we consider the interval A1 A2 excluding A1. So, now we consider interval epsilon excluding A1 but including A2, open interval, close interval. What will be the force at A2? At A2 there is no type 1 fiber. So, N1 into 0 plus N2 into P2. So, if we substitute N2 here, then it will be capital T G2 P2 by T2, right. Then the last interval epsilon greater than A2. There is no fiber, there is no bundle. So, what will be the force at that strain? 0. So, we obtain 3 expressions for force. One is this interval, second is this interval, and the third is this interval. So, what will be the force, what will be the strength of the bundle? Strength of the bundle will be the maximum of these 3 forces. This we can neglect, it is 0. So, strength of the bundle will be maximum of these two forces. So, we will write strength of the bundle will be, this is the symbol we used earlier, maximum of A1 A2, right. So, what is that? Maximum of capital T G1 P1 by T1 plus G2 S2 of S1 by T2. This is for this function, and for this will be T into G2 P2 by T2. Whatever will give maximum value, that will be equal to the strength of the bundle. Now, what will be, all right. So, here this T is common, constant, it can out of this maximum operator. Right. So, what will be bundle tenacity? Bundle tenacity is this, which is equal to maximum of these two. This will be expression for bundle tenacity. So, this is about the strength of the bundle. What is about the breaking strain of the bundle? Now, we will discuss that. Breaking strain of bundle. Two situations can arise. Breaking strain is denoted by this quantity. This can be equal to A1 if this T is equal to T2. So, if this is quantity is maximum, then the breaking strain of fiber type 1 will be equal to the bundle strain of the breaking strain of the bundle. Otherwise, breaking strain of the bundle can be equal to A2 breaking strain of the type 2 fiber, if this is equal to G2 P2 by T2. Right. Now, we would like to know the graphical representation of this expression, how this expression looks like graphically. So, this is the graphical representation of this expression. This. Let me explain you what is what in this diagram. X axis mass fractions are plotted. G1 denotes mass fraction of type 1 fiber, G2 denote mass fraction of type 2 fiber. When G1 is equal to 1 at this point, mass fraction of type 2 fiber is 0. Similarly, at the end, when G2 is equal to 1, mass fraction of type 1 fiber is 0. It has two y axes. This y axis we plot, this point is basically P1 by T1 and this point is higher P2 by T2. This point is S2 A1 by T2. So, this is basically specific stress of fiber type 2 at breaking elongation of fiber type 1. So, if we join this line, this dotted line, this line denotes G1 P1 by T1, this dotted line. Similarly, the line joining from 0 to P2 by T2 will give you G2 P2 by T2 and this is this line G2 P2 by T2, this line, right. Similarly, the line joining between these 2 points gives you G2 S2 A1 by T2. So, this dotted line gives you G2 S2 A1 by T2. And what is these two joining lines? This line gives you G1 P1 by T1 then plus G2 S2 A1 by T1. Okay. Now, what is of concern? Our concern is of minimum tenacity. We should not mix type 1 and type 2 fiber in such a manner that we should not arrive at minimum tenacity. That is basically is the concern while mixing. If we choose wrong blend ratio at which the bundle tenacity will be minimum, then we spoil the material. So, minimum tenacity is always is our concern. That means this point, so this will be the behavior of this bundle and then increase. This point is the worst point. At any case we must avoid this point, right. So, what do we see? We see 3 important points. First is this point, second is this point, third is this point. This point is very crucial. Now, this first this point can be obtained when G1 is equal to 1. So, in that case bundle tenacity will be P1 by T1. At this point G2 is equal to 1. So, what will be the bundle tenacity at this point? P2 by T2. These 2 points are easy, but the worst point is this. How will you find out the bundle tenacity at this point? So, the behavior of the bundle, tensile behavior of the bundle is this, and then it increases. At any cost we must avoid this blend ratio. So, this point can be obtained, is basically the intersection of 2 lines, this line and this line. So, this point gives is the intersection of 2 lines. That means, how will you find out this point? So, G1 is this line. So, G1, this expression will be equal to this expression. So, this line and this line. So, at this point G1 P1 by T1 plus G2 S2 A1 by T2 is equal to G2 P2 by T2, right. Now, let us write G1 as 1 minus G2. So, if we write G1 is equal to 1 minus G2, then if we club all G2 together in one side remaining on the other side, then we will be able to find out G2 is equal to P1 by T1 into P1 by T1 plus P2 by T2 minus S2 A1 by T2. Right. So, how will you obtain such a blend ratio? G2 is equal to P1 by T1 divided by P1 by T1 plus P2 by T2 minus S2 A1 by T2. And at that blend ratio bundle tenacity will be G2 P2 by T2. So, this is the minimum bundle tenacity which we must avoid in practice. So, in textile industry we should not mix 2 fibers in such a manner that at that particular blend ratio yarn tenacity is minimum or sliver tenacity is minimum or roving tenacity is minimum. We must avoid such a blend ratio under all circumstances, and this theory, Hamburger's theory, predicts what will be the blend ratio of 2 different types of fibers at which we obtain minimum bundle tenacity. What is interesting here to see that, come back to this graph, look at this here, G2 is equal to 0 and G2 is equal to 1. So, and G2 is stronger than G1, type 2 fiber is stronger than type 1 fiber, you have already seen this. This is type 2 fiber, type 2 fiber is stronger than type 1 fiber, P2 is greater than P1. So, we go on adding stronger fibers in the bundle. The bundle tenacity initially is reducing, it is lowest here, then it is increasing. So, what we observe from this figure is that very interesting, after addition of stronger fibers in the bundle, bundle tenacity can decrease. We are adding stronger fibers, however, bundle tenacity is decreasing. After certain point, it again starts increasing and finally it goes on increasing. So, the interesting part of this theory is that after addition of stronger fibers in the bundle, the bundle tenacity can decrease. Very much surprising. However, it is true. Hamburger's theory tells us about this. Now, two other situations can also happen, however, they are not of our concern. What kind of situations can happen? These two are also the possibilities. The curve can be something like that. Here highest here, lowest here, and it is continuously decreasing. In this case, lowest here, highest here, continuously increasing. They are of not our concern. Problem is only when initially it decreases, then it is increases. Initially it decreases, then it is increases. So, this is possible only when the stress strain diagram of the fibers is something like this. So, what we learn is that the stress strain curves of the fibers ultimately decide the tensile behavior of the bundle. Now, how this theory can be applied to yarn? So far we have discussed about parallel fiber bundle. However, yarn is a twisted fiber bundle. So, the question remains how this theory can be applied to yarn. If one wishes to apply this theory exactly the way it is to yarn, then there will be a huge mismatch between the actual results and the predicting results. One has to modify. How do you modify? Let us talk about that. How theory can be applied to yarns. What we will do in this case, the meaning of the symbols will be little different. P1 by T1 in Hamburger's theory, it was the tenacity of fiber 1, but in this particular case we will consider this as tenacity of single yarn 100% fiber 1. So, if the blend is say cotton and polyester, this means tenacity of 100% cotton yarn. Similarly, P2 by T2 will be tenacity of single yarn, but 100% fiber type 2. So, P2 by T2 will be the tenacity of 100% polyester fiber yarn, and then what will be by T2? This is the specific stress of single yarn, which yarn? 100% fiber 2 at strain A1. So, if we consider these three meanings in this manner, then we use this theory, you will be able to obtain the tensile behavior of the yarn. So, this modification or this consideration you have to follow if you wish to apply Hamburger's theory in case of yarns. So, now we will stop here. We would like to discuss in the next lecture numerical problems related to this module. Thank you very much for your attention.